Now this last section is on winds. Now we know that the air is kind of like a fluid. It kind of moves from place to place. Well, but that happens because air pressure causes it to move. Winds move from areas of high pressure to areas of low pressure. So most differences in air pressure are caused by the unequal heating of the atmosphere. I'm going to talk about this on the next slide because I'd like to actually draw you a diagram of how this works. So just quickly, these are just a couple of more vocabulary words that I want you to remember. This is the anemometer, which is a 3 to 4 cup mounted on the ends of spokes that spin on an axle, and this is used to measure wind. I have one in the classroom. Ask me about it. And then the other thing is the wind chill factor. Now, the wind chill factor, you've heard this on the news, although not so much here in Vegas, but this is where the wind actually causes an increased cooling, which changes our temperature, or at least what we feel of the temperature. Okay, so back to our wind currents. So again, you know what convection currents are. We've dealt with these when it came to water. We dealt with it within the liquids inside our earth. Well, these also actually happen with the air temperature above our earth as well. So if we have the surface of our earth, and I'm just going to draw that as a blue line because we're known as the blue planet, right? So this is our Earth's surface. Now, if I have heat coming down from the sun and it's heating this surface, so we're going to get some heat, right? What is going to happen to that surface? Well, the air over it, all these particles of air out here, are going to heat up. Now, what happens when it heats up? It becomes less dense. Now let's suppose that we have another surface over here, but this surface over here, it doesn't get as much heat. It only gets 1 arrow's worth of heat, right? So the air above it isn't going to get as warm. It's going to get a little warm, but not as much. Now what's going to happen to that? It's not going to get quite as less dense. In fact, it's going to become denser because it's going to be cooler. This one was warmer. So what's going to happen is we're actually going to have this air that's over here, which is cooler, is going to flow right at the bottom level. This air up here is going to be warmer. And actually, let's go ahead and change this color down here to blue so we know that this is the cooler air. So this air is going to be cooler, and this air is going to be warmer up here, and this is going to cause our convection currents to occur. It forces the warm air to rise because we've got that cool air that is going on underneath. Local winds, that's our next thing we're going to talk about. These are the ones that blow over short distances. This is a key word here, short distances, and it's caused by an unequal heating of Earth's surface within a small area. Another key word there is the small area, right there. Okay, now a couple examples of these are sea breezes. Now, the other thing we're going to talk about here is global winds. Global winds are ones that blow steady from a specific direction over long distances, and they cover a large area. I'm going to go into a little more detail here in just a minute on both of these. Two different forms of local winds are sea breezes. Well, that's one of them. And these actually happen when you have cold air moving in over water, and it comes over onto where we've got land over here, right? And on this land, our warm air moves up, and our cool breeze comes in and takes its place. And that's why you feel the wind when you're over by a body of water, such as the ocean or a lake. Now, the other one is land breezes. And land breezes are exactly the opposite. So if we have land and we have water, you're actually going to find the opposite happening, right? Where warm air is coming off of the water and cool air is actually moving off of the land. Back to global winds. The first thing we're going to do is we're going to look at this. Now imagine that the sun is out here and it's shining down into these regions. Now, which part of it is going to get the most intense amount of the sun's rays? That's going to be right here in the center, because this is where the rays are going to be shooting straight down from directly overhead, and it's going to be very intense in those areas. Imagine kind of like a magnifying glass if you were to focus the sun's rays on one spot. If you're looking directly down, it's going to be one tiny little direct spot. Or maybe think of this, actually even a better analogy would be if you think to like a flashlight. If you're pointing the flashlight straight down or straight at something, you're going to get a little circle. However, if you're pointing it at an angle, you're going to get a big oblong shape that happens where it's not directed. So you're going to get some fading towards one side, a little more intense at the one side. Now that is what is occurring at our poles up here. You'll notice they've got big, long, oblong shapes where the sunlight is hitting them. So it's not direct, and so therefore not as intense. Because of these sun rays hitting at these different things, you're going to find the temperatures are going to change at the poles. It's much colder at the poles than it is there at the equator. So what does this mean for our global winds? Well, it's all about convection currents. So these convection currents are occurring within our atmosphere, and especially with these global winds, right? So the temperature differences between the equator, where we have these warm air currents occurring, and the cold air currents that are occurring up here on the poles. Well, remember, these are density issues, right? So our warm air currents are going to be less dense, and our cold air currents are going to be more dense. So cold air sinks at the poles, and warm air at the equator rises. So pressure differences cause surface winds to blow from the poles toward the equator. Air flows away from the equator and toward the poles higher in the atmosphere, and these air movements produce those global winds. Now, the cool thing is that Coriolis effect. You briefly learned about this possibly back in the water unit. So let me write that word down. That is the Coriolis effect. So the Coriolis effect. So if our Earth did not rotate, right, if it was just sitting there, it didn't do anything, then these global winds would just blow in a straight line across the Earth from poles towards the equator. But because our Earth rotates, right, they don't follow a straight path. Instead, they curve. The winds curve around our Earth. Now, the interesting thing is that in the northern hemisphere, these winds will gradually turn towards the right. So that's this one here is going to turn this way, and this one here is going to turn this way. However, in the southern hemisphere, they're actually going to go the opposite direction because the wind is blowing towards the south. So these warm air currents are going to go in the opposite direction, as are our cold air currents that are going to go towards the left. Okay, this is the end of the atmosphere unit. Make sure that you have watched this twice. The first time, again, just watch. The second time, make sure that you have written down notes. Write your notes. And that is the end.